sponsor for doing the resiliency discussion and workshop this morning. That was really great. And I think that resonates with what I can say with what a lot of us in the Lablets are doing and thinking. So I think it's going to be a very positive thing going forward to try to connect those two efforts a little bit more. And then I'll start with an apology. I am department head when I'm not doing the fun research stuff I love to do. And so I had to go in and out just a couple of times, but I was able to be here most of the time. Okay, let me dive right into the talk. And this is a talk about a quantitative method to decide how to deploy monitors in a network system you're trying to monitor for security purposes. Actually, this is not Lablet-funded research, but it's NSA or DoD-funded research that's going on, and I think getting closer to what the Lablets are trying to look at. For a couple of you, I think 2 or 3 of you that were at the Dependable Systems and Networks Conference in Toulouse, France, in the last week in June. This is not as nice a location, so I apologize for that. But this was a paper presented at that conference, and so it's a relatively new work, and I thought I would present it here. So let me dive right in and just sort of set the stage, quite where to stand and have this really work. What are we trying to do, and what are we doing today? Well, again, there can be many different ways people make decisions about how to monitor their system for security or for resilience purposes. And this is just a cartoon that gives you a feeling at a high level of the way this happens today. So it's very human-centric. There's an administrator. The administrator may have and hopefully has very good domain knowledge about how to do monitoring, probably understands his or her system well, but probably does this in a fairly informal seat-of-the-pants way. Has a basket of monitors to deploy and deploys them in a certain way. Those monitors provide data to some security and information management system, a SIEM-type system. Those SIEMs generate alerts. The alerts somehow are viewed by the monitor, by the administrator, and decisions are made perhaps about how to reconfigure the system with respect to security. So if we just think of that as the problem on a very high-level way, what we'd like to do in this work is to come up with a more systematic and quantifiably justified way for how and where we should place those monitors. So the problem that we're working on is to determine which monitors of a whole set of monitors should be used, and we want to determine how they should be used to meet some particular requirements with respect to detection of intrusions in your system. What are the risks? The risks are if we over-provision monitors, there can be a lot of costs associated to that. There's a lot of data collection and storage, and in fact, it may not make the results better because you have a lot of data that may not be actionable. Of course, if you under-provision, you may miss important events within your system. And so this is what we're trying to do, and I should say that the basis of the motivation is a belief, really a conjecture at this point, that we want to build a set of, we want to build a capability to do monitoring where there may be quite diverse monitors that can provide complementary information about security events that we want to detect. Okay, so what we hope we're doing in doing this is to help administrators determine where they stand with respect to their monitors, and by doing some optimization or heuristics that approximate optimization, expose weaknesses in how the monitor is being done today and suggest better ways to do the monitoring. So what have we done in doing this? We've developed a quantitative cost sensitive. You'll see how the costs come in and some metrics come in for monitor selection that meets specific intrusion detection requirements. So there can be requirements that you put on with respect to a kind of set of metrics. There can be goals with respect to cost and other metrics, which you'll see in a minute. And then the algorithm makes suggestions about monitor placement. Okay, so what are the guiding principles? The guiding principles that the monitoring and the computing assets can be compromised. Compromised monitors will mitigate, or excuse me, can affect the ability to do detection. And you'll see we have a metric that we use in a relative sense to try to reason about our beliefs and the likelihood of compromise about particular monitors. And we have an ability to evaluate the usefulness of redundant monitoring in this system that can be used to mitigate this effect of potentially compromised monitors. Okay, so starting with an outline, we start with some domain knowledge about the system we want to monitor. We build a system model. This is something that, at least the way I'm going to talk about it today, a human does, but you can imagine ways so that you could take existing IDS system rules and automate the construction of these models, although we're not doing that today. From the system model, we then define monitoring metrics that we will use in order to do the optimization that I talked about. And then we optimally select the monitors, or from a practical point of view, we use heuristics to select a set of monitors. And we then quantify the goodness of that selection of monitors and perhaps tune the parameters once again. So that's really the cycle. And I should say that you'll see some results on the end for, I don't know if they're large or small, but from our point of view, reasonably large but synthetic networks. And the primary author, Uttam, who would probably even present this better than me, is spending the summer at IBM applying this methodology on some very large cloud-based systems. And so we're right now working with a real system in order to see how well this methodology works and how well it scales, and of course we'll end up extending it. Okay, so let's start talking about some of the terms. First, what do we, what happened there? Oh, I'm sorry, we'll just go on. First, let me define a few terms that we'll use in going forward. So first we have a set of monitors, and I think that's obvious what they are. They're a bunch of sensors that collect information about the systems. They generally generate log files, and in some sort of online way we're monitoring those log files and extracting information. We then have a set of indicators, and indicators are, if you will, the primitives of information that are extracted from the monitors that provide information about events. And the events then are the things we really care about. The events are the intrusions or the actions that are symptomatic about attacks that we infer from one or more indicators. And again, I'm not hung up on arguing that these are the right or the wrong terms. You could use the terms you like, but these three levels are what we're trying to do. And so what the goal then is to select particular monitors to provide a good detection of events subject to some metrics that we're going to talk about in a minute. Okay? And what we will see is that there may be multiple indicators, maybe from multiple monitors that signal particular events. So you can imagine then that a monitor will provide a set of indicators, and the indicators will be mapped to one or more events. And so that's in a sense the fundamental of what we're working with. I'll be using, at least for explaining the methodology, I'll be using a simple e-commerce web service, and I'll be imagining that there's a set of different monitors on that e-commerce web server. You can see here an example: MySQL query logs, Snort Network traffic monitor, Apache request logs. And again, our contention is, or conjecture is, that by monitoring from a diverse set of monitors, we can do better at detecting the events we're interested in the system. And this approach gives guidance about exactly how to do that.
So, Bill,
Go ahead.
an event may generate multiple indicators. Is that right?
Let's go back. A monitor will generate indicators, and I see. So the other way around. Yeah, that's right. So the event is caused by the intruder. The event will result in monitors generating perhaps multiple indicators. And then from the other point of view, and what the system does is it processes the indicators to try to alert you about events. And depending on what monitors you place, you may have multiple indicators that for a given event, you may have none, you may have one.
One indicator reflecting multiple events.
Right. I think so. I think so. Question? Yeah, please go ahead, Mary.
Yes, the difference between the red and the gray event certification there, does that have to do with confidence?
No, those are just two different events. Oh, sure. The question was: is there an indication of confidence in the detection of the event and the fact that one of them is red and one of them is gray? No, that's just intended to mean that those are two different events here. We'll talk about confidence in a minute when we get to the metrics, but right now I'm just saying in a deterministic way, and I imagine you could extend this, so it's the fact of the problem. In a deterministic way, these two indicators indicate that that event has occurred. And in a deterministic way, these two indicate that, and this one indicates that. And so this mapping, right now, what you see on this picture is done by a human, but you can imagine that these things would result, this could be, if this was a snort detector, these could be snort alerts right here. And if this is some sort of SQL log file, you may, in a programmatic way, be able to generate certain alerts based on what kind of operations are going on in SQL. And again, these, we believe, will be quite diverse, following the kinds of things that we've talked with you about before, but they may be symptoms of the same event. Okay? Okay. So here's a little example, and it's I don't want to dwell on it very much given time. Given that I'm the local host, I was given less time for some reason. But I will. We're trying to be nice to all of you, but we'll. Okay. Okay, so we have some attacker there. The attacker tries to attack the system. As the attacker moves through the system, one or more indicators will occur suggesting that the attacker has done things that are events of interest. Okay? So just to be concrete about this, you can see here a set of monitors. You can see the kind of indicators that those monitors may produce, and you can see the kind of events that we're hoping to be able to detect based on those indicators. Okay? And that just gives you an example of that kind of mapping. Got to keep moving or I'm not going to make it through. So the next part of the methodology is to define the monitoring metrics that we're interested in, and this will drive the optimization that we do. And we'll focus on that now. And we look at, and all the details are in the paper, I'm only going to be able to say this very quickly here, but we look at 3 different kinds of monitor utility metrics: coverage, redundancy, and confidence. We look at 1 cost metric, the cost of the overall monitoring system, and then we're going to formulate this, just to give you a look ahead, since we'll get there in a minute. We're going to formulate this as an integer programming problem. Some of the things that we specify with respect to the metrics being constraints, some of what we specify being things we optimize, and then we're going to look for the optimal set of monitor deployment given those metrics that we define. Okay, so the first one, coverage, and the mathematical description is in the paper. It's a rather simple metric in the sense that we look at what if we have a set of events that we wish to detect and we have a set of monitors that we deploy, to what extent does the set of monitors cover all the events we must detect? Okay, so if we imagine a system in which we consider just monitor 2 and monitor 3, we don't have monitor 1, so that event will not be detected, and then the coverage will be 2/3. I think that's a fairly obvious thing. But imagine we're showing you very trivial examples. We're thinking of systems that have hundreds of monitors and thousands of indicators, or even larger. Okay? We have a metric called redundancy, and that's the measure of redundancy is the number of different ways an event can be detected for a given set of monitors. So if we go back to our same system, the little example system we look at, and again, if we imagine in this case that we have selected for some reason monitor 1 and monitor 2, then we will not have these indicators, and the redundancy of associated with event 1 is 2, because there are 2 monitors that can detect it. If either of them detect it, the redundancy associated with monitor event 2 is 1, because there's only 1 monitor that detects that event, monitor 2 in that case, and the redundancy associated with event 3 is 0, because there's no monitor that detects that event. So you can see how that would be a metric you would care about. And then finally, the last utility metric that we consider is confidence. And again, looking at our little system again, we may have a certain trustworthiness associated with the results produced by each monitor. And again, we kept this deliberately simple. There's not a deep calculus of probabilities here. But if we have a belief in the trustworthiness of different monitors in a relative sense, and you can see what's assigned here, 0.5, 0.7, 0.3, higher number, more trustworthy. Don't think of these as probabilities. They happen to all be less than 1, but these are just values that you assign to these things. We assume then that the indicators take on the value of trustworthiness depending on the monitor that they are produced by. And then we assume as we go forward that the trustworthiness of the detection of the event will be the minimum of the indicators that are used to produce that. So in that case, you get a 0.5, so that detection will be with value 0.5. In this case, 0.5, because it takes both of these indicators to produce this event, so it's the minimum of the 2, and so forth. Okay, 0.7, 0.3, 0.3. So this indication is both of these indicators to produce this event, so we take the minimum. Okay, so then if we see what we have here, the confidence of detection for this system, the confidence of detection of event 1, in this case, will be 0.5. In this case, 0.7, because there are two ways to detect it. We can detect it the best of the two ways. And in the last case, 0.3, there's only one way to detect it, and we detect it with Oh, I'm sorry. Please go ahead. I'm looking more that way because I'm looking at that screen.
Why did you choose minimum and not like multiplying the two probabilities?
Well, because they're not probabilities. And you can think of different ways of doing this. So in this case, because you need both of these, a probability would be, a multiplication of probability would make sense if these were probabilities, these were independent, and we wanted to know.
But they're not.
The
So you're
case
saying they're not independent?
Well, what we're saying here is, I'm not making any statements about independence because these aren't probabilities. What I'm saying here is that I need both of these to work, and I have, think of it more from a fuzzy logic point of view, that this will work if both of them work, and I have some confidence there. So I take a minimum whenever I need both, and if I have two ways that I can detect this event, I take the maximum of these. Now one could imagine other algebras, if you will, I suppose, to do this kind of thing. But I think this makes sense given this notion of trustworthiness. Okay. I'm coming near the end. I think I still have enough time. The next, and then finally the cost model, and we won't spend, in the paper we talk about a lot of details about how the cost model works, but I think you can imagine that for a given set of monitors deployed in a system, individual monitors will have costs associated with them. They may have costs in computation, in memory utilization, disk storage, network computation, all sorts of things. They may have costs associated with their operation. So a cost to place them there, a cost with operation. And we come up with an overall cost metric for a given deployment. And you can do that basically in any way you want to do that. But that cost then is one ingredient. That overall system cost for that deployment of set of monitors becomes an ingredient in the optimization. Okay? So now I want to move on to the optimization part. And again, there are details in the paper that I can refer you to, or we can talk about afterwards. We want to answer these kind of questions, and I'll just go through. You might ask questions like, what is the minimum set of monitors to detect a given attack set or set of attacks, assuming no compromise? If you have certain cost constraints, what set of monitors will maximize the ability to detect a certain set of attacks? These kinds of things. So these are just examples of the kind of questions you can specify in this optimization framework. So what do? We represent detection requirements as weights on the various metrics that you can specify here, and we represent statements about minimum metric values as constraints. So if we take a set of these metrics and we say that we must have this metric attain a certain value, that becomes a constraint in the optimization. And if we have a metric that we are just trying to optimize, then we do that in the context of, in a weighted way, in the context of other metrics we care about. Here's some kinds of examples. We have a set of events, the same events we talked about. If we must detect exfiltration, we can put a minimum redundancy on this monitor of 1. If we have priorities about how we want to detect various events, then we can put weights on their redundancy in order to represent priority. If we just have a best effort for all others, then we can talk about a weight on a coverage metric. Okay, so this is an example of how you might assign these things. We then, in a fairly standard way, translate this to an integer programming problem. The objective function, again, is that weighted sum of metric values that we care about. The constraints become minimum detection requirements and the cost function, and then we need to solve this overall integer programming problem 0, 1, where think of it as a 1 is the monitor is included in the set, a 0 it is not, subject to these metrics. Okay. There are different ways to solve these problems. We could use a branch and bound approach to solve this problem exactly, but it's not very scalable. I think people who know optimization know this will not be a scalable approach. We could use greedy heuristic algorithm to approximate the solution of that algorithm. So we played around a little bit with exact solutions. They only work for small systems. They take a long time to run, but we're able to compare after long run times our case studies I'm going to show you about in a minute with respect to the heuristic, and the heuristic seems to work very well in this case. Okay, so what was our evaluation? Just to get to the end. The things that we're interested in is how this algorithm scales. How fast can we determine an optimal placement? Because ultimately we'd like to do this online and be changing the monitors in an online way as we learn more and the system runs. We want to vary the number of monitors, and we want to vary the number of events that we consider in the system. What we did is for each set of monitors and each set of events, we randomly generated 100 different models for each set of parameters. And we didn't do that in a particularly smart way, but we just wanted to look at sort of the variance and how well this works and the scalability. And then we created 4 different set of intrusion detection requirements. So what I mean by intrusion detection requirements are 4 different sets of metrics. And again, I don't have time to give you the details of all those, but they're available online in the paper. And we called those optimal deployment programs, which are the 4 different programs. And that gives us a feel of, for different metrics that we might specify, how does that change the solution time of the greedy heuristic algorithm? And we observe the results. And so, just since I see I'm about out of time, I'll just be very quick about this, but these are the 4 different metrics. This is varying the number of monitors that we consider in the system, so monitors in the hundreds, and these are the time in seconds to solve the heuristic to know how to place the monitors. This one that is what we consider to be a bad case, I don't want to say worst case, is one that occurs where there are a lot of minimum constraints in the system on with respect to the metric. So it puts a lot of constraints on so the heuristic algorithm tends to run in a poor set then. And those are the confidence intervals on the variance of the difference in the values for the different randomly generated networks that we did. This shows you as we vary the number of events that we care about detecting. So it gives you some feel in what we're doing. So I'll just conclude, because I see I'm at 28 of my 30 minutes. This is where we started. We now have a monitor deployment mechanism that can be used to make informed decisions about how one should place monitors with respect to certain detection requirements. We use that monitor deployment methodology to decide how to deploy monitors. We collect the results from those monitors in a standard way, but we now have an indication of the quality of what it is that we're collecting. Those then generate alerts, and the administrator can act on those alerts. Going forward, we'd like to work on what we call preemptive monitoring, and in fact some of this is going on this summer in the industrial work. And the idea there is to use results from the alerts to provide guidance in how to tune the monitor deployment methodology to get overall improvement in the quality of the monitor placement. So that was very fast, but right on time, boss David Nickel. So I'm not sure if I have time to answer questions, but thanks very much for listening. Go ahead, Jim.
Question. In this work, did you look at the choice for a single monitor of when you could put it at multiple places in the network? It seems like you could, in your formulation, you can model that as
right.
Multiple choices with a constraint that you can only put it in one of those.
Yeah,
places.
so that's a really good point, and I'm sorry I didn't make that clear. When I say monitor, I really mean monitor at a particular location, because the indicators that it generates will also depend on its location as well as the brand of the monitor. So it doesn't really mean snort is just one monitor. A snort sensor at a particular place defines a monitor, and it will have certain indicators that occur based on its placement and its type. So yes. So I think in the same way, I may have, when I say I have 500 monitors, there may only be 20 types of monitors or 10 types of monitors, but the 500, there will be a certain number of each of those monitor types put in different places. So it's essential, actually, I'm sorry I didn't make that clear. It's essential to the whole thing that the placement is very, I mean, that's what we're trying to do, right? We're trying to see, should I place it here or should I place it there, even if it's the same type. Thanks. I'm sorry I wasn't clear about that. Other questions?
All right, let's thank the speaker.
Thank you very much.